Okay, so today we're starting with the first law of motion, and this is about inertia. A ball at rest in the middle of a flat field is in equilibrium. No net force acts on it. If you saw it begin to move across the ground, you'd look for forces that don't balance to zero. We don't believe that changes in motion occur without a cause. Aristotle, the foremost Greek scientist, studied motion and divided it into two types: natural motion and violent motion. So natural motion on Earth was thought to be either straight up or straight down. Objects seek their natural resting places: boulders on the ground and smoke high in the air like clouds. Heavy things fall and very light things rise. Circular motion was natural for the heavens. These motions were considered natural, not caused by forces. Violent motion, on the other hand, was imposed motion. It was the result of forces that pushed or pulled. The important thing about defining violent motion was that it had an external cause. Violent motion was imparted to objects. Objects in their natural resting places could not move by themselves. Boulders don't move without a cause. It was commonly thought for nearly 2,000 years that a force was responsible for an object moving against its nature. The state of objects was one of rest unless they were being pushed or pulled or moving towards their natural resting place. Most thinkers before the 1500s considered it obvious that Earth must be in its natural resting place. A force large enough to move it was unthinkable. Earth did not move. According to Aristotle, what were the two types of motion? We'll pause. Alright, so I'm going to say his name wrong. Copernicus reasoned that the simplest way to interpret astronomical observations was to assume that Earth and the other planets moved around the sun. So the astronomer Nicholas Copernicus formulated a theory of the moving Earth. This idea was extremely controversial at the time. People preferred to believe that Earth was at the center of the universe. Copernicus worked on his ideas in secret. The first copy of his work, and I can't speak French, reached him on the day of his death, on May 24th, 1543. I can't say it. Anyway, so Nicholas Copernicus proposed that Earth moved around the sun, which is common knowledge now, but not at his time. So write down, what did Copernicus state about Earth's motion? Alright, so Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. Galileo, the foremost scientist of the late Renaissance in Italy, was outspoken in his support of Copernicus. One of Galileo's great contributions to physics was demolishing the notion that a force is necessary to keep an object moving. Friction is the name given to the force that acts between materials that touch as they move past each other. Friction is caused by the irregularities in the surfaces of objects that are touching. Even very smooth surfaces have microscopic irregularities that obstruct motion. If friction were absent, a moving object would need no force whatever to remain in motion. Galileo tested his idea by rolling balls along planed surfaces tilted at different angles. A ball rolling down an inclined plane speeds up. A ball rolling up an inclined plane in a direction opposed by gravity slows down. A ball rolling on a smooth horizontal plane has almost constant velocity. And so here you see you have your downward. The ball moves with gravity, or with Earth's gravity. And then here we're moving upward. The ball's going to move against gravity. In part A, you see the slope downward, the speed's going to increase, and then in part B, we'll have a slope upward, fighting against gravity and causing the speed to decrease. So then what happens when we look at C? On a level plane, it does not move with or against gravity. So what happens? Galileo stated that if friction were entirely absent, a ball moving horizontally would move forever. No push or pull would be required to keep it moving once it is set in motion. This would be the concept of perpetual motion, which is not possible. So Galileo's conclusion was supported by another line of reasoning. He described two inclined planes facing each other. A ball released to roll down one plane would roll up the other to reach nearly the same height. The ball tended to attain the same height even when the second plane was longer and inclined at a smaller angle than the first plane. So here you can see the diagram where the ball is rolling down the inclined plane, rolls up in the opposite incline, and reaches that initial height. And then again, where we have a lower angle, the ball still reaches that final position, even though it has to move at a greater distance to reach that initial height. And finally, if there is no friction, the ball would never stop. If the angle of the incline of the second plane were reduced to 0 so that the plane was perfectly horizontal, only friction would keep it from rolling forever. It was not the nature of the ball to come to a rest, as Aristotle had claimed. Galileo stated that this tendency of a moving body to keep moving is natural, and that every material object resists changes to its state of motion. The property of a body to resist change to its state of motion is called inertia. Alright, so let's think about this. A ball is rolled across a countertop and rolls slowly to a stop. How would Aristotle interpret this behavior? How would Galileo interpret it? How would you interpret it? We'll pause for a second to answer that. Okay, so Aristotle would probably say that the ball stops because it seeks a natural state of rest. Galileo would probably say that the friction between the ball and the table overcomes the ball's natural tendency to continue rolling. It overcomes the ball's inertia and brings it to a stop. Only you can answer the last question. Okay, so according to Galileo, when is a force needed to keep an object moving? Okay, so Newton's first law states that every object continues in a state of rest or a uniform speed in a straight line, unless acted upon by a non-zero net force. Newton's first law, usually called the law of inertia, is a restatement of Galileo's idea that a force is not needed to keep an object moving. Simply put, things tend to keep on doing what they've already been doing. So objects in a state of rest tend to remain at rest. Only a force will change that state. So here you have the display. It's common thought about as a magic trick. You have your dining room and the table set for dinner, and someone comes and can pull out the tablecloth, and the object at rest tends to remain at rest. Now consider an object in motion. In the absence of forces, a moving object tends to move in a straight line indefinitely. Toss an object from a space station located in the vacuum of outer space, and the object will move forever due to inertia. So blast blast of air from many tiny holes provides a nearly friction-free surface on an air table. If you slide a hockey puck along the surface of a city street, the puck soon comes to a rest. If you slide it along an air table where friction is practically absent, it slides with no apparent loss of speed. The law of inertia provides a completely different way of viewing motion from the ancients. Objects continue to move by themselves. Forces are needed to overcome any friction that may be present and to set objects in motion initially. Once the object is moving in a force-free environment, it will move in a straight line indefinitely. So the mouse says, notice that Newton's law of inertia and the equilibrium rule of chapter 2 basically say the same thing. When the change of force is zero, objects don't change their states of motion. Alright, so let's take a look at this cartoon strip. A body of rest tends to stay at rest. The dog runs away and he just falls off the cart. And then here we have a gentleman trying to stop the truck. Well, caveman really. A body in motion tends to stay in motion. He had no chance. Alright, so think about this. A force of gravity between the sun and its planets holds the planet in orbit around the sun. If that force of gravity suddenly disappeared, in what kind of path would the planets move? Pause the video and answer this question. Okay, so each planet would move in a straight line at constant speed. So what about this one? Is it correct to say that the reason an object resists change and persists in its state of motion is that it has inertia? We'll pause again and let you sort this out. So the answer is that we don't know the reason why objects persist in their motion when nothing acts on them, but we know that they do, and what we call this property is inertia. What is Newton's first law of motion? Take a moment and write it down. Alright, so the more mass an object has, the greater its inertia and the more force it takes to change its state of motion. So we're going to look at mass, a measure of inertia. The amount of inertia an object has depends on its mass, which is roughly the amount of material present in the object. Mass is a measurement of the inertia of an object. Definitely a vocabulary word. You can tell how much matter is in a can when you kick it. Kick an empty can and it moves. Kick a can filled with sand and it doesn't move as much. Mass is not volume. It's really important not to confuse mass and volume. Volume is a measurement of space and is measured in units such as cubic centimeters, cubic meters, and liters. Mass is measured in the fundamental unit of kilograms. And if it's in grams, you need to convert it to kilograms. Which has more mass, a feather pillow or a common automobile battery? Clearly, an automobile battery is more difficult to set in motion. This is evident of the battery's greater inertia and hence its greater mass. The pillow has a larger size, larger volume, but a smaller mass than the battery. It may take up more space, but its mass is going to be smaller. Don't mix those up. So mass is not a weight. Mass is often confused with weight. We often determine the amount of matter in an object by measuring its gravitational attraction to the Earth. However, mass is more fundamental than weight. Mass is a measurement of the amount of material in an object. Weight, on the other hand, is a measurement of the gravitational force acting on that object. So the mouse says that mass is a property within the body, and weight is an outside force on the body. That's the reason why it's very important that we use the concept of mass. So mass is inertia. The amount of material in a particular stone is the same whether the stone is located on Earth, on the Moon, or in outer space. The mass of the stone is the same in all of these locations. However, the weight of the stone would be very different on Earth and then on the Moon, and still different in outer space. Why is that? What changes? If you said gravity, you would be correct. The stone's inertia, or mass, is a property of the stone and not its location. The same force would be required to shake the stone with the same rhythm whether the stone was on Earth, or on the Moon, or in a force-free region of outer space. It is going to be just as difficult to shake a stone in its weightless state in space as it is on the weighted state on Earth. The mass hasn't changed in either situation, so the difficulty remains. We can divide mass and weight as follows. Mass is the quantity of matter in an object. More specifically, mass is a measure of the inertia, or laziness, that the object exhibits in response to an effort made to start it, stop it, or otherwise change its state of motion. Weight is the force of gravity on an object. Mass and weight are proportional to each other in a given place. In the same location, twice the mass weighs twice as much. Mass and weight are proportional to each other. They are not equal to each other. One kilogram weighs 10 newtons. It is common to describe the amount of matter in an object by its gravitational pull to Earth, that is, by its weight. In the United States, the traditional unit of weight is the pound. In most parts of the world, however, the measurement of matter is commonly expressed in the units of mass as the kilogram. At Earth's surface, 1 kilogram has a weight of 2.2 pounds. The SI unit of force is the Newton. The SI symbol for the Newton is in capital N. 1 Newton is equal to slightly less than a quarter pound. If you know the mass of something in kilograms and want its weight in newtons at Earth's surface, multiply the number of kilograms by 10. It's very important to remember this would be at Earth's surface. 1 kilogram of nails weighs 10 newtons, which is equal to 2.2 pounds. Away from Earth's surface, where the force of gravity is less, the bag of nails weighs less. Has it changed mass? Hasn't. So think about it. Does a 2 kilogram bunch of bananas have twice as much inertia as a 1 kilogram loaf of bread? About twice as much mass. How about twice as much volume? Twice as much weight? When weighed in the same location? So take a moment, pause the video, and answer this question. It's a big one. So to answer, 2 kilograms of anything has twice the inertia and twice the mass of 1 kilogram of anything else. It doesn't matter if it's bananas or if it's a loaf of bread, some socks, bricks. That doesn't make any difference. In the same location, where mass and weight are proportional, 2 kilograms of anything will weigh twice as much as 1 kilogram of anything. Except for volume. The answer to all of the question, except for volume, the answers to all the questions is yes. Bananas are much more dense than bread, so 2 kilograms of bananas must occupy less volume than 1 kilogram of bread. And if you don't know what the word dense is, think about it as compact. Bananas are going to be compacted into a smaller area than the more fluffy bread. And pause for a moment so you can write this down. Alright, so what is the relationship between mass and inertia? Take a minute and write down what that relationship is, and then we'll go over it. So the law of inertia states that an objects in motion remain in motion if no unbalanced force acts on them. Copernicus announced the idea of a moving Earth in the 16th century. One of the arguments against a moving Earth was consider a bird sitting at rest on the top of a tall tree. The bird sees a worm, drops down vertically, and catches it. It was argued that this would not be possible if the Earth moved as Copernicus suggested. The fact that birds do not catch worms from high tree branches seemed to be clear evidence that the Earth must be at rest. But objects move with the Earth. You can refute this argument using the idea of inertia. Earth moves at 30 kilometers a second. But so do the trees, so do the worms below, and even the air between. Objects on Earth move with Earth as Earth moves around the sun. Earth does not need to be at rest for the bird to catch the worm. Everything is moving at the same speed. If we flip a coin in a high-speed car, a bus, a plane, we catch the vertical moving coin as we would if the vehicle were at rest. We see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. I said that wrong. Basically, the horizontal motion of the coin would be the same before, during, and after. So the vertical force of gravity affects only the vertical motion of the coin. Only that up and down motion. I remember my first physics class, they stated that think about a fly flying around in a car, or a mosquito, since we live down here in the south. You have a mosquito buzzing around. You could be driving 80 miles an hour. As long as the windows are all up, that mosquito flies around without any problem. But you roll the windows down, and of course the mosquito is going to come to a rest because of the air resistance. Alright, so back to the coin concept. So flip a coin in an airplane, and it behaves as if the plane were at rest. The coin keeps up with you, inertia in action. Inertia safety. More than 3 million kilogram steel balls hanging at the 87th floor of the tallest skyscraper, and I think I can't say the name of that, help stabilize the 101-story building against vibrations caused by earthquakes or strong winds. And I'm going to have to look that up. So how does the law of inertia apply to objects in motion? Take a minute, write it down, we'll go over it in class and answer it.